Okay, this is the Chapter 10 free response. We'll say this is number 1, part 2. This is the back side of that worksheet. All right, let's see if we can figure out this number 6. Notice that they're all number 6s. The probability that the number 6 on your AP test will be a series question is about, well, let's say about 95%. All right, so here's a function defined by a power series, and they were nice enough to write out the first few terms for us. They want us to find f prime of 0 and f double prime of 0, and then determine whether f has a local maximum, minimum, or neither at x equals 0, and give a reason for our answer. So first, I think we better find the derivatives. The derivative of this power series is, derivative of the first term is 0, second term is negative 2 over 3 factorial x plus 4x cubed over 5 factorial, etc. It doesn't take long to see that all these terms are going to have x's in them, so the derivative at 0 is 0. Right? Second derivative is, the derivative of this is negative 2 over 3 factorial plus 12x squared over 5 factorial, etc. And when I plug 0 into that, everything gets knocked out to 0 except for the constant term, which is negative 2/6 or negative 1/3. So is that a local maximum, minimum, or neither? I think we actually might have seen this part of this problem in a previous incarnation. So this means that there's a horizontal tangent line, and this means that it is concave down. So if you've got a horizontal tangent line and it's concave down, then this must be a maximum. Why? Because f prime of 0 is 0, and second derivative is negative. That's why. Part B. Show that 1 minus 1 over 3 factorial approximates f of 1 with error less than 1 over 100. Well, this is an alternating series, so error approximation is easy. So we want to show that, so f of 1 is approximately equal to what you get when you plug 1 into the series. And if you plug 1 into the series and you only take the first two terms, well, you get 1 minus 1 over 3 factorial. And then this would be the error term. So the error is less than the next term, which is x to the 4th over 5 factorial. And here we're talking about, we're plugging 1 in, 1 to the 4th over 5 factorial, which is 1 over 5 factorial is 120. And that's less than 1 over 100. Now, why is this true? And you must say this to get full credit here. This is worth a whole point. The error is less than this because it's an alternating series and the terms are approaching 0. It might seem like totally obvious, like that's why you pick the next term, right? But you must say this. You can't bring up this error is less than the next term business unless you state that it's an alternating series and the terms are going to 0. Therefore, the error is less than the next term. So that's what you need to do. Please don't be lazy. It's going to cost you a point if you don't say that. Part C. This is interesting. Show that y equals f of x is a solution to the differential equation x times y prime plus y equals cosine x. Let me write that down. So the x times the derivative of y plus y is equal to cosine x. Well, let's see if we can figure out that. Now, the derivative of y, that's just the derivative of our series, right? And the derivative of our series, I'm going to put the x here, is negative 2x over 3 factorial plus 4x cubed. We started to find it up here, right? I'm just doing the same thing. Over 5 factorial minus, I'll do one more term, 6x to the 5th over 7 factorial, etc., plus y, the actual series itself, which is 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. Let's just manipulate this side of the equation. If I multiply in here by x, I get minus 2x cubed over 3 factorial plus 4x to the 4th over 5 factorial minus 6x to the 6th over 7 factorial plus 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. Okay, let's try to simplify this and combine what we can. I've got a 1 here, and then I've got these two terms. Minus 2x squared over 3 factorial minus x squared over 3 factorial. So I've got minus 2x squared minus x squared over the same denominator. That's minus 3x squared over 3 factorial. And here I've got plus 4 plus 1 over the same denominator, so that's plus 5x to the 4th over 5 factorial, minus 6 minus another 1, that'd be minus 7x to the 6th over 7 factorial. And simplifying this, the 3 here cancels out the front number of that factorial. 3 over 3 factorial knocks the 3 off, so that's just x squared over, that's only 2 factorial now. 5 knocks off the first 5 and makes that 4 factorial, and 7 knocks the first 7 off, makes that 6 factorial, and that equals the series for the cosine function. Pretty cool. All right, the last one. Function f has a Taylor series about x equals 2 that converges to f of x for all x in the interval of convergence. So they're not telling us, it just converges to all the x. Well, of course it does. That's the definition of the interval of convergence. That's sort of a silly thing to say. The nth derivative of f at x equals 2 is given by this formula, and f of 2 equals 1. So we're going to have to make this one from scratch. So let's see if we can do that. Let me just write this down. So we're doing the series at x equals 2, which means, remember, that means all of our terms are going to look like, they're all going to have x minus 2, etc., right? They're all going to have like x minus 2's in them. And the derivatives, the nth derivative is given by, nth derivative at 2 is given by n plus 1 factorial over 3 to the n. And f of 2 is equal to 1. All right, just as an exercise here, I'm going to go ahead and write out what the recipe is for making a Taylor series. So the Taylor series at, well, at any number, but let's just write it out at 2, would be f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 over 2 factorial, right, that's squared, plus f triple prime of 2 times x minus 2 cubed over 3 factorial. It's just like a Maclaurin series, except instead of zeros, all of the x's, instead of x's, these are all x minus 2's, and instead of plugging in 0, we're plugging in 2. And they wanted the first 4 terms and the general term. So let's see if we can do that. Well, f of 2 is 1. They gave us that. Plus f prime of 2 is 2 plus 1, that's 3 factorial, over 3 to the n. This is the first derivative, so that's 3 to the 1 over 3 times x minus 2. Oops, what am I doing there? Yes, sorry, this is the first term. That's the nth derivative. Looks good. Okay, now I'm plugging in, this is the second derivative. So to find the second derivative, I plug 2 into this. That's 2 plus 1. I think I messed up somewhere, didn't I? That should be 2 factorial, shouldn't it? Because I was plugging 1 into this for the first derivative. Sorry about that. Now I'm finding the second derivative, so I'm plugging in 2 into that. So that one is going to look like 3 factorial. It's a second derivative, so that's 3 squared now, times x minus 2 squared, plus, when I plug in for the third derivative, I plug 3 in here, it gives me 4 factorial over 3 to the 3 times, I forgot something else too, didn't I? I forgot the 2 factorial. Sorry. And then here I've got x minus 2 squared cubed over 3 factorial. Yes, that looks good. Okay, there's the first 4 terms. So you can see what's happening here. Just ignoring that one for a second. Looks like our factorials are going up by 1 each time. The power of 3 is going up by 1 each time, and the factorial on the bottom is going up by 1 each time. Now, you don't have to simplify this, but in this particular case, it's going to be easier if we do. So I'm going to simplify. 1 plus, that's 2 over 3 times x minus 2, plus 3 factorial over 2 factorial just leaves a 3 there. That's 3 over 3 squared. I'm just simplifying the factorials. And then that 3 factorial knocks out everything except the 4. 4 over 3 cubed. And you can see what's going on. It's going to make it a little bit more easy for us to write the general term, which will be, let's see, if we call this the 0th term, if this is the first term, then this number here, it would be n plus 1. Right? I'm starting with 0. You could start it with 1. That would work too. This is 3 to the n, if this is the first term, right? And this is x minus 2 to the, if this is the first term, to the 1. And it does not alternate. Right? You can test when you plug in 0. That would be 0 plus 1, which is 1, over 3 to the 0, which is 1. And then x minus 2 to the 0 is 1. So that works for the first term too. All right. B. That was all part A. Part B, they want the radius of convergence. The radius of convergence, right? Not the interval, but the radius of convergence for this series. So we have our general term now, so we want to find, using the ratio test, we want to find the limit as n approaches infinity of the n plus 1 term divided by the n term. Oops, the n term, sorry. It looks just like this upside down. So the n plus 1 will be down here, and the 3 to the n will be here. All right, simplifying that, we've got what? I've got one extra x to the, or x minus 2 here, which actually should be, let me scratch that real quick. That should be outside of the limit, right? X minus 2, because the limit is about n's approaching infinity, not x's, so that goes outside. And then I have 3 to the n plus 1 and 3 to the n. That gives me an extra 3 on the bottom. And then I've got n plus 2 over n minus 1. So look at that, 1/3 is n plus 2 over n plus 1. That limit right there is just 1. So 1/3 times 1, that's 1/3 times x minus 2. And that means I need to sandwich this in between -1 and 1, doing a little bit of algebra here, multiplying each piece by 3, and then adding 2. So the radius of convergence, the center is at 2, so it looks like the radius is 3. That was fun. Part C. Let g be a function satisfying g of 2 is equal to 3 and g prime of x is equal to f of x for all x. Find the first 4 terms of the general term for g. Alright, let me bring this back. So look, if we want to find g, we have to find antiderivatives here, right? So g of x is equal to the antiderivative of the f of x series. Alright, where is that f of x series? Here it is. I think this is in its simplest form here, right? So let's find that antiderivative. So g of x is equal to the antiderivative of that. I'm going to leave a little space here in case there's a c, and there actually is a c, right? They told us that g of 2 equals 3, right? That's going to be our first term. G of 2 equals 3, so that's our first term. And then the antiderivative of this is x. The antiderivative of this, bumping up the exponent by 1, x minus 2 squared, dividing by the new exponent. Dividing by 2 is going to get rid of that. And then bumping the exponent up by 1 and dividing by the new exponent. You see that's going to happen every time. That number is going to get canceled out. Looks like that is the series for g. Those are the first 4 terms. And the general term is going to be, if that's the 0th term, then the first term, oops, that should be, tricky. You know what? For this to be an actual Taylor series, that needs to be an x minus 2, doesn't it? So if that's an x minus 2, that is a little tricky. And think about this for a second. If g of 2 is equal to 3, when you plug in 2, you're supposed to get 3. Oh, that's still right. That's okay, so that's right. I just didn't put my x minus 2 there. So that's still okay. So when I plug in 2 into all these, I get 3. So that's good. I just forgot to put the x minus 2 here. All right. That works. So it is almost like that term had its own little plus c here, but we knew it had to be. It has to be an x minus 2 there, and that will make it easy to figure this, right? That just makes the first term 3. Now, what is the general term? If this was the first term is x minus 2 to the n, does not alternate, over 3 to the n minus 1, right? Because there are 0 3's here. And if you plug in 0, that actually, believe it or not, that gives you the right first term, doesn't it? That's awesome. Because if you plug in 0 for the 0th term, that gives you 1, and 3 to the negative 1, that would, on the bottom of this, flips it back up. So that is absolutely correct. That is cool. All right. Last part. Part D. Does the Taylor series for G, as defined in Part C, converge at x equals negative 2? Give a reason for your answer. Does it converge at x equals negative 2? Let's see. At x equals negative 2. That is outside of the interval of convergence for the last function. So I think probably it doesn't, because f didn't converge there. Excuse me, didn't converge there, but let's plug it in and see what happens. We get 3. That'd be every single one of these is going to be negative 4, right? Plus that'll be negative 4 squared over 3 plus negative 4 cubed over 3 squared plus negative 4 to the 4th over 3 cubed, etc. What kind of series is this? That is a geometric series. What's the multiplier? What are we multiplying by every time here? Well, every time here. Did I miss a term here? I did, didn't I? There should be a negative 4 here. But the point is, it's a geometric series, and you see what's happening every time on the top. We're multiplying by negative 4. Every time on the bottom, I'm multiplying by 3. And this is not in between 1 and negative 1. And those are the values where geometric series converge. Negative 4/3, no convergence. All right.